Back to this morning session. I have a couple of information for you. Today the coffee break will be during the poster session, so we will have to go to the Lavoisier building for the coffee break and for the final poster view session. And also, but for this afternoon everything will be held here, so we'll stay in this building. The first morning session is now open, and Gunther will be the chairperson of this session. So please, Gunther.
So, good morning. I also welcome you to the morning session of the last day of this meeting after this very nice conference dinner. And it's my pleasure to announce the first lecture given by Palacin about functional catalysis for hydrogen production and uptake and oxygen reduction. So basically the topics of yesterday are continued in this morning session.
Thank you. Thank you very much. So, good morning. I hope everyone recovered from the dinner and what after. Okay. In his talk on Monday, George Weisheitz brilliantly demonstrated that hydrogen could be a possible way of fighting the global energy crisis we are facing now. Not as a source of energy, because it's not one, but as an energy carrier or energy storage solution. And more especially, it is envisioned as a solution to store energy which is produced, electricity which is produced by non-permanent sources like solar energy or wind energy, to store it until we need it. So the needs we have at the moment are be able to efficiently transform electricity into hydrogen. So that means it's an electrochemical process, splitting water, reducing water into hydrogen, or afterwards using hydrogen as a source, as a secondary source of energy, which means oxidizing hydrogen into water, back into water, and produce electricity. And both methods are electrochemical, and both methods require the same kind of compound to do this change, this chemical reaction efficiently, which means efficiently in terms of number of electrons required and the price of the system. At the moment, some solution exists, and by far the best catalyst, the best electrocatalyst, which works in those two reactions, reducing water into hydrogen and oxidizing hydrogen into water in fuel cells, is platinum. And because platinum has the lowest overpotential for doing those reactions, the overpotential is what you had to apply extra from the thermodynamic value to get the job done. And some other catalysts have larger overpotential than platinum, and so they are not suitable for a practical application. The problem is platinum is very expensive, as any man here who, I don't know, dreamt of buying a ring made of platinum to his wife knows. And platinum is not expensive only for speculation reason. It's expensive because it's very rare. There is not enough platinum on the Earth to envision a real hydrogen economy based on platinum electrocatalysts, either in electrolyzer or in fuel cells. So there is an urgent need of other electrocatalysts. And some people are working on decreasing the amount of platinum. This is not enough as a solution. Some people work on alloying platinum with other metals. Some people are working on new other metals, but no solution has been produced yet to replace really platinum in terms of quality, general term, of the electrocatalytic activity. So there is another idea that emerged, I think more than 10 years ago, which is trying to get help from nature. Because surprisingly, even if hydrogen is not a natural asset, some living organisms are producing hydrogen. These are bacteria, which works in anaerobic condition, and they are using hydrogen also to store energy. And this is made using natural catalysts, of course, which are called hydrogenases, which is not surprising. And thanks to the work of some structural biologists, especially Juan Fontecilla in Grenoble, the structural organization of some of those hydrogenases has been explained and deciphered. And what was found was that besides all the protein pocket, which is the surrounding medium here, you have a catalytic site, which is generally based on a simple metallic complexes, generally bimetallic, either iron-iron or iron-nickel, and not surprisingly, the metals that were chosen by nature are the ones which are the most present on the surface of Earth. And so, now that people know that, there is a strategy that has been developed to design new catalysts, which is a biomimetic strategy, which means copying the structure of this natural site into, for example, that molecular catalyst, which has been designed and synthesized in the lab. And you see that the distances between the metal ion, the surrounding of the metal ions, and so on, are close, not exactly the same, but close to what can be found in a natural enzyme. And so this kind of system are tested in solution with respect to the reduction of water into hydrogen. And there is a second strategy, which is a little bit further, which can be called a bio-inspired strategy, which not rely on copying fully the structure of the enzyme, but copying what is necessary to get the job done when you know the mechanism of the reaction. And in that case, the molecules that are designed, like this one by Dan Du Bois, or this one in Marc Foncave's group in Grenoble, are just trying to gather all the necessary sites for producing the reaction in an efficient way. So it's what we call a bio-inspired strategy. And so those catalysts are tested in solution, and you have there the potential where the electroreduction occurs in organic solution generally. Okay, the problem is those catalysts are very efficient in solution, and more precisely in organic solution because they are not soluble in water. But it's very difficult to compare them directly to the reference, which is still platinum, because platinum is never used in those conditions. Platinum is used in a solid state, deposited on carbon black. So it's an electrode material which works in a solid state and which works in water with acidic water. Okay? So in order to compare and to see whether this strategy can give us solutions, you have to immobilize those catalysts onto surfaces. And this is where our group entered the game. And for that, we have a strong collaboration with the group of Marc Foncave and Vincent Artero, who is here in Grenoble for the catalyst. Our idea was to immobilize one of those electrocatalysts onto a high surface area conducting surface. And we chose a network of multiple carbon nanotube physisorb on ITO. Okay, so you have here the ITO surface, and this is the network of carbon nanotube. Why? Because we expect from this a high specific area, okay, because it's nanomaterials. We know that this has a metallic behavior, so the conductivity between the ITO and the grafted complex would be good. And we know how to functionalize those electrocatalysts. And we even tested two competing strategies for that. Covalent grafting I will be discussing more in detail, and pi stacking that we will see in the end. So what we need from that is the highest catalyst loading as possible to get the more current from the same experiment, high electronic transfer between the real electrode and the catalyst through the network of nanotubes, and of course a high stability because we want something that works more than 1 second. So I don't think I have to discuss this at length because numerous papers have been given during this conference on that, but we are mainly relying on electroreduction of diazinon salt for the covalent grafting on carbon nanotube. This works very well. It goes in irreversible grafting. It goes, of course, this polyaryl layer growth that has been discussed at length also during this conference. The only small problem is that diazo are poorly stable, but it's not a big issue, and we already know how to face that. So, just a small focus on the question of covalent grafting, and you know it's a main debate in the community at the moment, and I just want to focus on three examples besides other that have been given to prove that we have a covalent grafting, but we also that also show that we not yet know exactly how it works. This is a paper from Richard McCreary that I don't know if he's still here, but he was here yesterday, in 2004, who showed that on copper oxide, you have a covalent bonding through the oxygen. That means that you have a copper-oxygen-carbon linkage between the surface and the diazinon salt. This is very recent by McDermott. It's still in press. And in that case, it's coming from the Raman experiment on spontaneous grafting of diazinon salts on gold nanoparticles. And in that case, it seems you have, at least from the peak that is given here and from the simulation that is also on the paper, that you have a direct metal to carbon bonding. Okay? And this is unpublished result we got from our group that shows in the same kind of experiment, but not on nanoparticles, that you have gold to nitrogen peaks that we explain as keeping the diazo group during the grafting. This is spontaneous grafting, it's not electrochemical grafting, okay? But that means, just this slide, just to explain that this debate is not closed, and we are still trying to understand how those funny molecules are really behaving, either spontaneously or when you fuel electron into the solution. Okay, we are using in the lab electroreduction or spontaneous reduction or chemical assisted reduction of diazinon salt for many different uses. I will of course discuss only on that one, but I will just give you a short focus on that one because it could be another solution for the problems I'm talking about today. And because one solution for finding new electrocatalysts would be to use directly the natural enzymes. And so we also need to immobilize those natural enzymes on a surface to check their reactivity. And for that, diazinon salts are also very efficient because you can very easily do this. This is shown as a monolayer, but of course it's not one. It's just for sake of simplicity. This can be done in one step from the diaminobenzene compound, which is purely commercial. You do not need to isolate diazinon salt. You can do it in situ. You get this aniline surface, and then you can recreate diazinon salt on the surface. And from that, it is a highly electrophilic surface that can react with any nucleophile. And it can work with molecule. It can work also with biomolecule, which we know are full of amino and thiol group. So you can spontaneously absorb and covalently graft biomolecule onto surfaces this way using only very simple and commercial compound. And another advantage of that solution is those grafted diazinon salts can be killed very easily by shining UV light. As you can see here, at room temperature, it's almost stable for 2 hours in ambient condition. This is at 45 degrees, so, and this is after shining UV, it's a couple of, let's say less than 1 minute in normal UV, and you kill all the diazinon that are shine. That means that if you shine light through a mask, you can pattern very easily, and so you keep where the mask was useful, you can keep the reactivity of the diazinon salt, and so, as shown here for proteins and for DNA, you can pattern the grafting of protein or pattern the grafting of DNA. These are infrared imaging on one of the peak from the proteins or one of the peak of the DNA. Okay, and we check also for the case of glucose oxidase that the stability and the activity of the enzyme is kept. This is not a rule. In some cases, the grafting of the biomolecule will kill the activity. Okay, but this is right. This is the same for any covalent grafting, except when you are able to target one specific site of the biomolecule. Which is very more difficult, and so it's not general. In that case, it's a general method, very easy, but in some cases it won't work because you will kill the activity because of the way the molecule has been grafted spontaneously on the surface. Okay, but this could be a strategy to immobilize natural enzymes, but unfortunately those enzymes are not stable in ambient condition. I told you that those bacteria are living in anaerobic condition, and generally those enzymes are killed when you go into oxygen rich medium. So it's not a way, at least until we get natural enzymes that are able to work in ambient condition with oxygen, this will not be a solution. So we go back to our strategy to immobilize the enzyme, the molecular catalyst onto carbon nanotube. This to show you that we are able to graft very easily diazolam films, polyaryl films onto carbon nanotube. This can be checked by SEM, by XPS, and so on. I mean, this is very classical and has been published a lot of time. There is, of course, an effect on the solubility. And more interesting, we started our work by checking the electrical connection between the carbon nanotube and a redox probe, in this case ferrocene, by using this particular diazolam salt for making the polyaryl growth. And this one has been chosen because we need a real amine, primary amine reactivity in order to graft, and on the second step, which is a purely chemical one, to graft the redox probe and afterwards to graft the catalyst using this activated ester which gives us a high yield reaction. And this does not work with the diamine, the aromatic diamine I showed you before, because the reactivity of the amino group is not enough because of the aromaticity. So we use that. Okay, this is grafted electrochemically. This works very well. And then we did the second step. This first figure here shows you the measurement of the amount of extra surface we get from using the multi-wall carbon nanotube network. So this is just checking of the amount of signal we get from the reduction of the diazolam salt on the ITO, the pristine ITO surface, on the same surface gold, the same area gold surface, and on the multi-wall carbon nanotube deposited in ITO. And the ratio is 160, which means that we have 160 times more surfaces, active, electroactive surface in the case of the multi-wall carbon nanotube network versus ITO. And this is after the grafting of the redox probe, and you see that the peaks shows clearly that we have an immobilized redox probe, and so we have, and also that we have a very nice electrical connection between the carbon nanotube, and so we have also the ITO and the redox probe. So this is pretty good for what we want to do, which means putting here a catalyst, an electrocatalyst. The first example we have been trying is coming from the biomimetic strategy, and this is that one. This is a very simple molecule that can be made in one step for reaction between the lipoic acid here and the precursor, which is a diiron 9-carbonyl complex. And this is a pretty nice mimic of that natural catalyst which structure has been demonstrated by X-ray. And that one, after the same way as we grafted ferrocene in the last slide, that one has been grafted onto carbon nanotube, and you have here in the black is the infrared spectrum of that compound, and you see here the two peaks arising from the carbon monoxide. Okay? And after grafting, it's a blue one. You see here and here the two same peaks, which means that we have immobilized carbon monoxide-rich compound onto the surface. And this is also confirmed by XPS, where you can see here this peak is arising from the carbon monoxide, while this one is arising from the amide group, which is necessary for the grafting. And of course, we have iron on the surface, which proves that we have grafted this complex. And after that, we check the stability under electrochemical condition. And on the first scan, we have a nice reduction peak arising from the iron. The problem is, after the second scan, the peak is fully different. And after that, we check the infrared after the second scan. And this is the red one here. And you see that it seems that we have lost the carbon monoxide ligands. And this is confirmed also by XPS, where the amount of this peak, which is coming from the carbon monoxide, but also for some carbon to nitrogen compound within the diazone, the polyaryl group, has also fully decreased. In the same time, the iron peak did not change. So it seems that we had a degradation of the complex, which has been replaced by an iron-rich complex again, but in that case, there is almost no interesting electrical activity. So that means that this complex is not stable enough in the condition we are doing the experiment to be used as an electrocatalyst. Okay, so after that unsuccessful attempts, we decided to rely on the more robust electrocatalyst that has been published at the moment we started this work, which is this one, which has been proposed by Dan Du Bois, and I showed you on probably the second slide on my talk. And we just modify it on the periphery to get activated ester to be able to do this chemical grafting onto the carbon nanotube, which has been modified by the diazonium salts. We checked that the electroactivity is the same as a parent compound that has been published by Dan Du Bois. That means that those modifications do not change anything into the redox activity. And this is not surprising because the center pocket has not been changed. And more interestingly, those amine group here, which are supposed to protonate during the reduction process and bring this proton close to the hydride that has been created in the first step of the reduction, those are not changed with respect to the parent compound. We also check the electroactivity in solution with respect to increasing amount of proton, and you see, as for the parent compound in solution, that the current is increasing regularly, almost linearly, with the amount of protons in the organic solution. So that means this compound is almost as efficient as the one that has been published by Dan Du Bois. So after that, we decided to graft this compound onto the carbon nanotube with the same strategy as I showed you before. So first, electrografting of this polyarylamine layer, and second, a chemical reaction with the compound I just showed you to get a grafting of the compound onto the carbon nanotube. And we check by the presence of phosphorus, which is the ligand of the nickel. We check the presence of nickel, and all this works correctly. And we were also able, from the electrochemical activity without any proton in solution, to get one measurement of the surface catalyst concentration, which is around this value here. Okay. So the most interesting is this part, of course. What happens when we increase the amount of proton in this organic solution? In that case, the solution is organic, so the source of proton is protonated DMF. And you see this is without acid. It's the same as I showed you just before. And increasing the quantity of proton in the solution, you are increasing the current, as shown here. Okay? So that means that we have the electrocatalytic activity we expected from this electrode material. We had to check something. Multi-wall carbon nanotube, as some single-wall carbon nanotube, are produced by reduction on iron catalyst. And so many carbon nanotube sources are full of iron into in the center of the core, and so we had to check whether this electroactivity was not coming from the carbon nanotube. So these are the same peak I showed you here, and this is the electrocatalytic activity for the carbon nanotube network without the catalyst. And you see that, of course, you have an activity, but the overpotential is almost 600 millivolts higher for the case of carbon nanotube. So the result we showed here could not arise from the carbon nanotube. It's arising from the catalyst we deposited on top of the carbon nanotube. So the results, the figures we got from this analysis is that we have a very low overpotential, 200 millivolts, which is close to what is found in solution. We have a 94% Faradaic yield, and we got in this experiment 20,000 turnover in 1 hour, which means that it's pretty stable and correctly fast as an electrocatalyst. So this is the way we expected the mechanism. It's of course a very simple, I would say simplified mechanism. The next step, as I told you, and this is what we really wanted to do. We did not want to stop at the nice result I just showed you. We wanted to compare those electrocatalysts to the reference, which is platinum. And for that, we had to make an electrode which is similar to the one that is used in electrolyzer based on platinum nanoparticle deposited in carbon black. And for that reason, we made this way using Nafion and using a paste of carbon nanotube with the electrocatalyst grafting on it. We made a membrane, and we checked the activity of that membrane in a nitrogen atmosphere, okay, using, in that case, this was done in water with sulfuric acid as the source of proton. So it's a main difference with the one I just showed you. And this is on the left part, on the light green part here. This is the current we got in red, in blue, sorry, from this experiment, which means that we are getting current, actually. So we are reducing proton into hydrogen in those conditions. And what is also very interesting is that when we change the atmosphere from nitrogen to hydrogen, in that case, and applying a positive potential, and this is a red curve, in that case, we got the reverse reaction, which means that we are also able to oxidize hydrogen into water, back into water, into proton, actually, with the same catalyst. So as many metal catalysts, this one is working in both sides, which is very interesting because it could be used both for producing hydrogen and for using hydrogen into a fuel cell. This is not a comparison. The comparison is here. And, of course, the first comparison is not very nice. These are the current versus the current density versus potential for the same electrode without catalyst, so with the carbon nanotube alone, our system and the platinum system on carbon black. And you see that there is 1 to 2 order of magnitude in the current density in the comparison between our catalyst and platinum. This is not very nice, but there are some reasons for that. And the main one is that the amount of catalyst in our case is far lower than the one of platinum, at least if we count in a number of metallic atoms that are present in the case. So finally, we checked the stability before change. We checked the stability of this system, and you see that over 10 hours, with that surface concentration of nickel, we got 100,000 turnover during those time, and no change in the activity during those 10 hours of experiment. So the system is stable, the system works well, but the system, at least because of the concentration of catalyst, this is one of the main reasons we think explain this low activity. We are still lower in activity and in current with respect to the platinum reference. So we decided to check what can happen with another way of immobilizing the electrocatalyst. And this relies on pi stacking. You know that carbon nanotubes are fully aromatic systems. So by changing the catalyst, this is the same catalyst, so we decided to check with the same. And we modify on the nitrogen, we modify with pyrene group, which are highly aromatic systems that stick onto the surface of nanotube. And so this works very well, and you can see from the electroactivity from this curve that the immobilization works very well. And the difference between this immobilization and the former one, in that case, you can repeat the experiment by adding new carbon nanotube, and so you can expand the quantity of catalyst onto the surface just by repeating the experiment, which is not possible with the electrochemical one because you are facing some problem of accessibility of the reactor of the catalyst to the internal part of a 3D electrode, the 3D electrode, which is the carbon nanotube network. So this one is allows you more easily to increase the surface concentration of the catalyst with respect to the covalent electrochemical grafting. So here are the curves recorded both on reduction and oxidation part at the same condition as I showed you before. So this has been to be compared with the one I showed you on the 2 slides before. You see that for the reduction part, the reduction current are almost the same as the covalent grafting reference. For the oxidation part, we are slightly lower, but we still have some electroactivity for the oxidation of hydrogen. And as I told you, with this non-covalent strategy, we are able to tune the amount of the loading of the catalyst by repeating the experiment, and so we were able to reach concentration where now the amount of catalyst onto the surface can be compared to the amount of platinum that we have on our reference system. And in that case, the current we are measuring now is pretty close to the one we have with platinum. So that means that the difference I showed you before, this sort of 1 to 2 orders of magnitude into the current density, was mainly arising from the amount of catalyst which was deposited on the surface, not from an intrinsic difference in activity between the electrocatalyst and the platinum. And finally, and this looks like a sort of gift that you get in the end after a lot of efforts, we decided to check how our electrocatalysts behave in presence of CO. Why? Because CO is the main poison of platinum. It's almost the only one which is troublesome for platinum system. And you can see here with a commercial membrane loaded with platinum at this amount, that after, let's say, 20 minutes in the presence of 50 ppm of CO, there is almost no activity left into the system. And on the contrary, with our system, the one I just showed you with pi stacking, the stability is still the same after this time into the same atmosphere. So that means that our system is tolerant to CO, which is interesting at least until hydrogen could be produced without CO, because at the moment hydrogen is mainly produced by reforming methane, and some CO remains into the hydrogen. So that means that the hydrogen that can be used right now into fuel cell is poisoning for platinum. So it's a problem if we have to reach a real use with that source of hydrogen. If the source of hydrogen is changed from electrolysis of water, for example, it might not be the same problem because CO should not be there. Okay, so this is a very nice result. Those are some conclusion on that part. And so I think I convinced you that using taking inspiration from nature can give you some ideas of how to find alternative ways to make electrocatalysts for reduction of proton, production of hydrogen, and also using hydrogen to recover some electricity. But we have still a lot of work to do to improve the catalyst, to improve the amount of catalyst deposited on the surface, because it's based on local reaction, on chemical reaction on surface, so we need to increase the amount. And just to finish, I just want to give you some very recent results we got for the other part of a fuel cell. On a fuel cell, you need to oxidize hydrogen, but you also need to reduce oxygen. And when you look at the possible way to reduce oxygen, there is one efficient one that you need to keep, which is this one. It's a direct 4-electron reduction. This is the one you want to provide. And there is not very wanted one, which is passing through hydrogen peroxide with two electron reaction in a row. And that one is not preferred at all because this compound is not very nice for many of the catalysts that are used. So the idea is, of course, to reduce the role of 2-electron pathway. In this topic, platinum is also the best catalyst known. So it's difficult to face always the same time, always the same enemy, I would say. So we are trying to capitalize on our knowledge onto modification of carbon nanotubes to get high loading of catalysts, and we are trying to check the activity of those catalysts which are already known for this kind of reaction. And so we are making, by simple absorption of those aromatic system on carbon nanotube, we are making membrane. And in this study, we are comparing different sources of carbon nanotube, different ways of treating them to remove carbon black, for example. And we are also comparing all those compounds which are based with either porphyrin or phthalocyanine. And so I won't discuss all the curves, but what is interesting to get is that the multi-wall nanotube are clearly behaving more effectively than the single one or the double wall nanotube. The one which were treated with nitric acid to clean them and in some cases open the conductivity are more efficient than the pristine one, which are directly coming from the synthesis. And among the catalysts, the iron phthalocyanine is clearly more efficient than all the others. So this is just a result. We still not have any explanation on that. What is interesting is that we get a very low overpotential with respect to the platinum on carbon reference. So that means we are in the right way in that case. This was done in alkaline electrolyte, and in acidic it's almost the same. And you see that the number of the average number of electron in those processes are in that case not that bad with compared to the reference, which is 4 electron. This one is a little bit less. So in all cases, the multi-wall carbon nanotube, which has been treated with inacidic media to remove everything which is not really carbon nanotube, are behaving very well, despite the fact that in some cases with acidic treatment you are creating some COOH or COH, alcohol or acidic groupment on the periphery of the tubes. But this, in a whole, is increasing the activity of the catalyst with respect to the pristine nanotube. So this is just to give you a flavor of what we are doing at the moment on that subject for the other part of the fuel cell. And so we are expecting to make a fuel cell which is fully organic at the moment, which could be nice, just for fun in that case, because I'm not sure that the activity will be enough to be interesting and economically. And so after that, I want to thank the organizer and more precisely Jean-Christophe and Feti for giving me the opportunity to be on the same poster in the entrance of the university, on the same poster as George Whitesides, as Michael Gretzel. I mean, I'm still shaking on that. And I thank you for your attention. And on behalf of all the people who did that, I hope I gave you some interesting issue on what we are doing. I just want to thank more precisely first Marc and Vincent. Vincent is here and he will be giving a talk this afternoon. They are the colleagues from Grenoble which are working on the electrocatalyst design. And the work has been mainly done by Alan, who is also in the room. The work on the electrocatalyst has been now Joshi is working on that, and I think and this work has been supervised in my group by Bruno and in Grenoble by Vincent. Thank you very much.
Thank you very much for this nice lecture, and the talk is open for discussion, and we have enough time to ask a number of questions. Please.
Yes, it's a very nice work.
Thank you.
Coming back to let's say, the pyrene system, I have a question in two parts. How do you check the amount of pyrene on your carbon nanotubes versus the interstacking of pyrenes between themselves in the solution?
We are not checking this directly. We are checking the electroactivity of the final electrode material. So after washing, so we think that by washing, we removed whatever is not deposited on the carbon nanotube. But of course, washing is not sure that we have been removing everything. But anyway, after those washing, we have a material that can be deposited onto the Nafion membrane to make the final membrane assembly. So if some of the catalysts are still imprisoned into the system, well, they may be active or not because they're probably too far from the electrode to get the current, to get the electrons coming from in case of the reduction. But, well, they are still there. It means that we might have a small difference when we count the surface area, the surface density of catalyst by electrochemical way and by, let's say, XPS, something like that. But you know the error margin of both are enough to be in the same range anyway. We did not find any major difference when trying to measure the amount of iron, for example, by XPS and the amount of catalyst by electrochemistry. So that means that we are, I mean, if there is a difference in that case, it will be in the same way.
Yep.
A second part. I noticed that in your catalyst you have 4 pyrenes per catalyst.
Yeah.
Is it a strategic, let's say, way of doing that, or it is because it is more easy to do that? Because if you had only one, you could check that.
Alan, do you want to answer? Both. The first one is to be sure. For example, it's part of the answer of your previous question. If you have more pyrene, you have more chances that the catalyst will be reacting with the nanotube. Okay? And the second, of course, is that it's easier to synthesize.
Okay, you make this what you call PDP, the one with the diazonium.
Yeah.
How stable is that? Because I mean, we tried to make
I showed you, I guess.
a polystyrene, and that said poof.
Okay.
And what do you mean by kill? What is the mechanism, and what do you get?
I think this one. Okay.
Yeah.
So you are troubled about that. Maybe I get okay. This is the stability, and this is measured by the size of the infrared peak from the diazonium. Okay, the 2001 and so on.
How close are they?
What do you mean at close?
How many do you have together? I mean, what is the loading of your surface?
This is This is done by electroreduction of the corresponding diazolam salt. Okay, so I don't remember the thickness in that case because it depends on the number of cycles or the time of the electrolysis. I don't remember the thickness in that case, but what we know is that the major part of the free amino group that can be seen in the infrared before this reaction are not visible after. So a large majority of the amino group that can be found in the infrared here are transformed into diazolam after this reaction. And the stability here is in the lab, in the absence of light, of course, okay, so in the dark. But after 2 hours, you almost lose nothing in the intensity of the infrared peak coming from the diazolam group.
Do you lose only the diazonium group, or do you, when you put UV light, or do
when we put UV light, it depends on the media. I think that in a normal condition, you have enough water adsorbed onto the surface when you shine light to transform the diazolam salt into phenol. Okay. I think this is the main product you get because you have enough OH group around. I think during UV light, we are, at least that's what we think, you are evolving dinitrogen and creating a cation. And so any nucleophilic compound passing around will react with this cation, and if you have water, it will be OH. Okay.
Okay.